Okay, welcome guys. So this is a video describing and reviewing everything that we covered in Chapter 8, specifically 8.1. So in this pamphlet, or in this packet, we talked about the first 4 objectives of this chapter. So remember that this is basically going over trigonometric identities, specifically for use in trigonometric proofs. Okay, so the goal is to, of course, try to solve these proofs the most efficient way possible. So throughout this specific objective, Mando, you're gonna have to chill out. Okay, you're really gonna have to chill out. So throughout this specific objective, or pair of objectives, we have all of the proofs, and I'm just going to scroll through until we get to the first type of problem. Now you'll notice that this font is a little bit different than the font that you can find on Schoology, but that's only because I had to change programs, and changing programs, the fonts didn't match up. So it kind of looks weird, but either way. Objective 2 is all about substituting known identities to verify proofs. So this is the simplest way that you can prove something is true. And remember that every proof that you'll see on this pamphlet is really an equation. Okay, so the idea of proving something is just saying, yes, okay, in fact, these two things are equivalent to one another, right? So here we have the first one, tan x times cotangent x equals 1. And what you may want to do is have that identity proofs sheet that's in Objective 1 next to you. Either print it out or just pull it up on the screen next to you. Just so that way you can reference it while I go through these proofs. Okay, that being said, here we have a very simple proof in that it only takes one substitution to prove. Before I start this, let me just add a few things. First, notice that little sentence above the proof talking about when you're verifying an identity, you're only going to work on one side of the equation. You're not going to work on both sides simultaneously. You're not going to do any algebra within your proof as far as moving something to another side, dividing, etc. You're strictly going to be using the identities in some way on one side of the equation. Now, what I did specifically in this packet was create a column to notify you which side we're working on. So you'll notice that on the left of this table, there's a blank column saying identity used. And that's supposed to say, okay, we're using the left side of this proof and plugging in identities to it in order to make it look like the right side. Okay, so this right side, immediately we can just go in and just plug in 1, since that is not going to change. Now, on our left side, the first proof that I'm going to use is going to be a reciprocal proof. And the reason why is because I noticed that we have a tangent and a cotangent right next to each other. Now, I'm sorry that my handwriting is kind of sloppy. This pen isn't the best, but I'll make do. So what I was saying was we have a tangent and a cotangent right next to each other. And you always want to keep in mind where you're trying to go. So I'm trying to get this side to equal 1, which means that we should have some cancellations of some sort. If we have cancellations, that means that there should be an identity that relates tangent and cotangent together, in that they cancel out, meaning that they should be together in an identity. The only identity that shows that is the reciprocal identity, which is, in fact, tan is equal to 1 over cosine, or vice versa. So I can plug in tan x for tangent, but cosine I'll replace with its reciprocal, 1 over tangent x. Okay, tangent times 1 over tangent, I make these types of analogies all the time in class, is the same thing as 2 times 1 over 2. Okay, that means that we can treat these just like we treat any numbers, any variables, whatever. They're words, but remember, they're also just functions. So with these functions, we can cancel them out just like we would cancel out this 2 times 1/2, and that would give us our 1. And there is our first proof. Moving on, we have our second proof, which you can see is a little bit different visually. But even though visually it's a lot different, we're going to use the same technique that we did for the last proof. So notice first of all that we're still using that left side for identities, meaning we're going to change that left side. And also we have one more box. So every proof, every identity that's on this page and any page to follow, I have already solved. And I've done so in a certain amount of steps, and that's how many boxes that I kind of show for each proof. So that means I solved this one in 3 steps, which is one more step than the last identity. Alright, to begin this, one thing I want to point out just for general proof solving, whenever you see squares, usually, not every time, but usually, you want to look at the Pythagorean identities. So in this case, we have secant squared, cotangent squared, and tangent squared. If we look at our identities, you'll see that there is one Pythagorean identity that has both excuse me, secant squared and tangent squared. Now, that identity looks like 1 plus tangent squared theta, and that's equal to secant squared theta. Now, 2 points to make here. The first is that theta is just a variable, meaning that in your problem, it may not say theta, it may say, for example, 3x. But this identity is still going to work for trig functions with theta as 3x. We just need to pay attention to that and make sure we keep it consistent throughout the problem. Second thing, this identity does not look exactly like our problem. So what we want to do, either physically by writing it out on a scratch piece of paper or mentally, is we want to perform algebra on the identity itself. Now, the algebra that we're going to do is always going to be simple, subtracting, adding, dividing, whatever. And in this case, we want to have a negative tangent. So what I'm going to do is I'm going to subtract tangent squared over to the right side. Sorry, did not mean to put that equal sign. Let me try to erase that. Okay. And when we do so, our new identity is going to read 1 is equal to secant squared theta minus tangent squared theta. Again, sorry about this pen. For some reason, it's not really working with this application, but anyway. This is our new identity. Now, notice that it may not look exactly like this because there's a cotangent squared in the middle, but we still have a secant squared minus tangent squared. That's the important part. That means we can take this secant squared minus tangent squared, which is exactly the same secant squared minus tangent squared that's up here, and replace it with just a 1. So the right side, we're going to write cosecant squared because that hasn't changed. Our identity we used was Pythagorean, and I just abbreviate this as Pythag. And then, as I said, we replace the secant squared minus tangent squared with a 1. Okay, that may be hard to read, but it says 1 plus cotangent squared of 3x. Okay, at this stage, we now have something that looks very similar to a Pythagorean identity that's separate from this Pythagorean identity, and that is exactly 1 plus cotangent squared theta. So we're going to use Pythagorean again, and we replace this 1 plus cotangent squared theta with cosecant squared theta. Alright, So notice that I was about to write theta, but we need to keep in mind that in this problem, theta is 3x. Also, I realize now that this additional step that I was going to write was, I was going to rewrite the first equation with secant squared 3x minus tangent squared, oops, one second. Sorry about that technical issue. I was able to basically rework the problem with a separate app. So it's a little bit neater, and these are the correct steps that I used beforehand. So notice that I rearranged the problem first, so that way I could then substitute our secant squared minus tangent squared with our 1 and keep the order, and there wasn't a cotangent squared in between. So once you do that, again, you can just use the Pythagorean identity. 1 plus cotangent squared is equal to cosecant squared. And there you have it. So that is our second proof. So let's move on to the third. Here we have our third proof. 5 sine y plus 2 cosine y squared plus 5 cosine y minus 2 sine y squared. So here we have to do the crucial step of factoring first. And once we factor, we'll be able to see what kind of identities we can use to solve this type of problem. So in this problem specifically, these 3 steps won't have an identity. Now, I can't speak for those of you who may be watching and aren't in my class, but for those of you who are in my class, whenever you're trying to solve these types of proofs and you're not using an identity, I don't require you to write anything down in these boxes. The only thing you really have to fill out is this left and right side, as long as you're not using an identity. So in this case, I wrote factor, but that's more pedagogical. It's not saying you have to do this each time for like a test or an assessment or whatever. Okay, so starting to factor this out, we have a perfect square here. I'm sorry, not a perfect square. Maybe just call it a perfect square. Either way, when we FOIL this out, what we're going to have is we're going to have a squared plus 2ab plus b squared for our first squared here. And then for our second one, since there's a minus sign, we're going to have a squared minus 2ab plus b squared. And these will all be found on Objective 4 notes, but for now, we'll just leave this here. So foiling all of this out, we get 25 sine squared of y plus 2 times 5 is 10 times 2 is 20 sine y cosine y. And then we have b squared plus 4 cosine squared y. Okay, I'm going to pause this, fill out the rest, and then come back. Okay, here we have the second part foiled out. And one thing to note about factoring is almost always after you factor, you can cancel / combine like terms. This is almost always the case. I can't say it's definitely always the case, but for most of the time, once you factor, you can cancel or combine like terms in some degree. Okay, so here we have the positive 2ab and negative 2ab, so those two will, in fact, cancel each other out. Side note, if you don't know this, sine and cosine, the order of them does not matter. I could have had sine cosine or cosine sine, and it still would have canceled out. That's just because a times b is still equal to b times a. Alright. Now, as far as combining like terms, we have a 25 sine squared here, and a 4 sine squared here. Likewise, we have a 4 cosine squared here and a 25 cosine squared here. Since they're all positive, all of those numbers will add together, so the 25 plus 4 gives me 29 sine squared y, and likewise for cosine. Anytime we have anything with a common factor, what we want to do is we want to factor out that common factor and try to use an identity on either the common factor itself or the stuff that's left in the parentheses. So in this case, when we factor out that common factor of 29, we will have something in the parentheses that we can use an identity on. And if you look at your identity sheet, you'll notice that that should be the Pythagorean identity. That identity is cosine squared plus sine squared is equal to 1. So this becomes 29 times 1, or in other words, just 29. And we're done. Alright, so with that third proof, we move on to our objective 3, which is changing sines and cosines to verify an identity. Or I should say changing two sines and cosines to verify an identity. So this is, I think, one of the most versatile methods of solving proofs. It can be used in most cases because everything can be related back to sine or cosine in some fashion, whether that be through the quotient, the quotient or the reciprocal identities. So let's just kind of jump into it. Our first identity that we're going to try to prove is going to be this tangent cotangent minus cosine squared identity. So if we look at this right hand side, notice that our identity used column is on that side, so that is the side we're going to change. And our left side, sine squared t, is just going to remain that. And again, t is just a variable. We can treat it as theta. So the first thing that I notice is, again, we have a tangent and a cotangent next to each other. You might remember that from the first proof, but if you don't, we're going to solve it differently anyway, so that's okay. Like I said, I want to change everything to sines or cosines. So in the case of tangent and cotangent, we're actually going to have to use the quotient identity to change those to sine or cosine. And if you're looking at your sheet, you'll notice that tangent is sine over cosine, whereas cotangent is cosine over sine. Okay. Hopefully you see that cosine cancels out as well as sine, leaving us with just a 1 minus cosine squared here. If you don't see how that is, maybe pause the video, think about it for a second, and come back to it. But now we have 1 minus cosine squared t as our right hand side, and what we want to do is compare that to our Pythagorean identity, sine squared plus cosine squared is equal to 1. So we're looking at Pythagorean identities again, because we have a square and a 1. So if you see both of those together, you should probably look at one of those identities. In this case, what we have to do again is we have to rewrite it, again using some algebra. So here we see that sine squared is equal to 1 minus cosine t squared, meaning that I can replace this whole side with just a sine squared t. And since we use the Pythagorean identity, we say Pythag right here, and we're done. Okay, so from here on out, what I want you to start doing is pausing the video once I show the proof and trying to figure it out yourself. Once you have figured it out or you get stuck, then play the video and walk through it with me. So in this one we have a quotient of a bunch of different trig functions, or not a bunch, but two on top, one on bottom. And again, we want to use the method of changing everything to either sine or cosine. So that means for secant and cosecant, we're going to use the reciprocal. And for cotangent, we're probably going to use the quotient. Now, sidebar. If you haven't noticed already, there are a lot of different ways that you can go about doing this proof. In fact, the first step I see in this proof, I can think of like at least 3 first steps that you can take, and there's probably more. All of those steps are totally legitimate and are okay to take, as long as you do them correctly. And what I mean by correctly is that you just can't make up math, right? You have to use the identities in a mathematically okay way, an acceptable way, if you will. Okay, so let's start this out by first erasing this arrow, and second, just choosing one of those steps. So I'm going to choose to do the least complicated one and break up everything into separate functions itself. So I'm going to rewrite this as secant theta times cosecant theta times 1 over cotangent theta. Okay, now when you get good at proofs, you'll be able to do that sort of thing in your head. You'll just be able to kind of like see it as 3 separate things. But since we're just starting out, I'm going to use that or this empty box as an opportunity to rewrite everything as separate. Now we can kind of individually change them for sines or cosine. So we're going to use the reciprocal identities for all of these first. Okay, that means that secant becomes 1 over cosine. That means cosecant becomes 1 over sine. And that means that cotangent becomes, 1 over cotangent becomes tangent theta. Okay. Now, since we have a tangent hanging in there, we can use the quotient identity to change it to sine over cosine. And we hopefully see that sines cancel out, the cosines do not, so we're left with 1 over cosine squared. And we can use the reciprocal identity to change this to secant squared theta. I kind of forgot to fill these in, so I'll do that now. But hopefully that makes sense. Technically, I think I used one more box than I usually do because I wrote this out instead of kind of seeing this in my head, but hopefully it gave you a better understanding of how I went about solving this. Okay, again, try to solve this without my help at first, and then clear the video and watch me walk through this. Okay, so here we have negatives. First thing I want to just make a note about this is you want to take care of these first. So take care of the negatives first. Negatives first. Technically, you can solve this entire proof without taking care of the negatives first, and you can take care of them later. But I think it's good practice to take care of them first. So when it comes to the first identity that we're going to use in this specific problem, we're actually going to use the even and odd identities, or I should say properties. Now, if ever you use 2 separate identities in the same line, that's okay. Just make sure you write both of those identities in the column. So in this case, cosine is an even function, meaning that it just becomes cosine theta. And sine is an odd function, meaning that the negative is taken out of the parentheses and put in front of our function. Okay, so now we want to again use that strategy of turning everything into sines or cosines. So we're going to take the reciprocal identity to change our functions like cosecant to 1 over sine. And I skipped over this because one thing that again we can kind of do in our mind is to separate these out. And if you notice, this is 1 over secant times cosine, so we can change the 1 over secant to just cosine. So this becomes cosine theta times cosine theta. So our sines cancel out, but our cosines become squared. And hopefully by now you can see what identity I'm going to use here. We're going to use a Pythagorean identity. However, kind of doing mental manipulation or doing some sort of manipulation to the identity on a scratch piece of paper, hopefully you see that in order to get cosine squared minus 1, what I actually have to do is keep cosine where it is and swap sine with this 1. What that does is it makes 1 negative, but it also makes sine negative. And that is why we have negative sine squared theta. A note that I can make about this specific problem that I saw my students doing was they kept trying to make this negative sine squared. They thought, okay, well, I see a sine, I see a negative, so this has to be the negative sine squared. It's understandable why they tried to do that, but it's also a very bad habit to get into. You never want to look at something and say, okay, this has to be my answer, so everything else must be 0, or everything else must cancel out, or whatever. Worry about doing each step correctly. You will eventually get what you need to get, right? There's eventually going to be a step that gets you what you should get, because all of these identities are true, right? So don't hyper focus on part of it and say, okay, this has to be what my answer is, because you'll get stuck. Okay, so that all in all completes the 8.1 objective 1 through 3 video. If you have any comments or questions, please let me know, and be sure to check out the objective 4, 5, and 6 video next.